Hello everybody and welcome back to the session about visualization of NumPy arrays and regression. So visualization of NumPy arrays works actually in the very same way as with lists. So this should be a repetition of what we already know about line plots, scatter plots and histograms. And we will also have a look at regression analysis, and it works very easy with NumPy, and we not only perform linear but also polynomial regression. And last but not least, we try to approximate an assumed functional relationship in a given set of data points with the Taylor series expansion techniques. And this is definitely a more advanced topic in this course, but we will see it later in detail and hopefully understand how it works. Alright, so let's first of all import NumPy, and then we import matplotlib.pyplot as PLT, and we have to set matplotlib inline here in Jupyter Notebook, and we use the style seaborn. And then we create a normally distributed random numbers, 10,000 numbers, with mean 5 and standard deviation 2. So we get an array Y with 10,000 elements. And then we make an histogram. So we pass our ND array Y to the histogram. We set bins to 100 and we label the data. Then we enlarge the size of the figure with PLT figure fixed size equals 10.6. And we set the title of our histogram to frequency distribution of Y. And we call our X label Y and our Y label frequency. And also we enable a legend in our histogram. So let's run the cell and see what we get here. Yeah, so we get here an histogram with normally distributed numbers, and it already looked like a bell-shaped curve. So we have 10,000 data points, and if we further increase this to 100,000 or 1 million, it would be a very good bell-shaped curve. And we can also here plot a vertical line into our graph. And the vertical line is at the value of the mean of our ND array. So this gives us a quite good impression. So we determined in our random process that the mean should be 5, and the mean of our random numbers is actually 5 roundabout. Alright, and there's a function called np_linspace, and what np_linspace does, it creates evenly spaced numbers over a specified interval. So we specify here, let's press Shift-Tab. We specify here our start point, it's 1, our stop point, it's 10. And then we say we want to have 50 evenly spaced numbers between 1 and 10. So let's see what we get here. So by default, the number is 50, but we set it here to 10. So we get 10 evenly spaced numbers in the interval between 1 and 10. And we get actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So and let's create 1000 evenly spaced numbers in the interval -10 to 10 and call it X. So now we have a NumPy array X with 1000 numbers. And this is very helpful when we want to plot a graph or a function. So with linspace we can create many X values that are close together, and then we can calculate a functional relationship over our X values. And there we can calculate Y values depending on our X values and the functional relationship. So let's assume here we have our functional relationship. So Y is 3 times x to the power of 3 minus 2 times x to the power of 2 minus 5x minus 5. So now this is, we already know, vectorized operations. So for each element of our ND array X, we get a corresponding Y value here. Here we have the array Y. So now we have X and Y values, and we can actually plot these in a 2-dimensional graph. So we plot X and Y. And there you can see here our function which we determined here. And we can also define another function. So for example, the sinus function. So Y is the sinus of X. So now if we repeat here the plotting, so now Y stands for the sinus of X. And here we get the sinus plot. Alright, so far we had a histogram and a line plot, and let's go on with a scatter plot. We generate 20 normal distributed numbers with mean 10 and standard deviation 2. and reshape those into 2 rows of 10 columns. Let's call the matrix M. So we have 2 rows, 1 row, 2 rows with each 10 elements. And then we slice our matrix and we call our first row A and the second row B. Now we have 2 arrays with 10 elements each, and then we can make a scatter plot of A and B. Okay, so let's see here. So our first point is, so A is on the x-axis and B is on the y-axis. And for example, let's see, so we have our first point, it's on the x-axis 7.8 and on the y 8.6. So 7.8 and 8.6, so this is this point here. And maybe another point. So we have the point with on the x-axis 12 and on the y-axis 9.8. And this should be this point here. And what we can do now, we can do a linear regression that fits a straight line into our graph here. And we can do this with the function np polyfit. So we have to pass our 2 arrays A and B. And we have to determine the degree of our polynomial. So 1 stands for a linear, 2 stands for quadratic function, and 3 stands for cubic, and so on. But we will see this later. So now let's run here the cell. And what np polyfit returns, actually, it returns the polynomial coefficients from the highest power to the first in a tuple. So we have here minus 0.15 and 12, and this gives us actually the functional relationship here of our linear regression. So the functional relationship is here actually b equals 10.51 minus 0.1599 times a. So this is here the intercept of our function, and this is the first coefficient. Alright, so now let's create some x and y values. So we create x values with linspace. And we can create our y values with the function np polyval. So np polyval creates y values given some x values and the polynomial coefficients reg1, which we calculated here with np polyfit. So let's calculate both x and y values, and then now we can plot our linear regression line. So we plot it in our graph where we also have our scatters. Here our points, and there we plot in our linear regression line with our x and y values. So let's execute here. This is the linear regression line. So a regression line is a line that best fits to the data. What does it mean? So in very simple words, so each point has a distance here from its actual y value to the regression line, and what the regression line does is actually minimizes, to say, the sum of all distances. So in detail, it minimizes the sum of all squared distances. So in easy word, it's just the line that best fits here into our data. Alright, so what we can do now, we can make also a quadratic regression by setting the degree to 2. So let's run it here. And then we get here the polynomial coefficients. So 16.98 is the intercept, 0.05 is the coefficient with the highest power, and the functional relationships looks like this here. And we can also calculate the cubic regression, so with the polynomial degree 3. And this gives us a functional relationship between a and b in this manner here. So you have here the polynomial coefficients. And then we can also plot in our cubic and quadratic regression in our graph. So it's already here. And let's plot both. So in here you can see this is the graph for the quadratic regression, and this green graph here is the graph for the cubic regression. And the more you increase the degree of the regression, the better the graph fits our data points. So the average absolute distance between our cubic graph and the data points is much lower than the average distance between the data points in our linear regression graph. And last but not least, we can have a perfect regression where all data points are on our regression graph. So the distance between our data points and the graph is 0 and of course therefore minimized. And in our case we have 10 data points and we can reach a perfect regression with a polynomial degree of 10 minus 1, so with a degree of 9. So let's set here perfect regression and we set NP polyfit. We pass our arrays A and B and we say, okay, our degree should be the length of A and B, of course, minus 1. So now we get here 10 polynomial coefficients and now we can plot our data points and our perfect regression curve. And there you can see the regression curve perfectly fits here our data points. And you can see here, so we have a different scale than here with our scatters. So it's here 9 to 14 on the y-axis and here it's 0 to 800. So therefore let's zoom in. Yeah, and there you can even better see that our regression curve perfectly fits our data points here. So what is a perfect regression useful for? So in our case we created two arrays A and B that are actually independent and randomly created. So there's definitely no functional relationship. And not only our perfect regression curve, all of our regression curves do overfit the data. So they indicate a relationship where there's actually none. And overfitting is a real problem in data science. But on the other hand side, if we are sure that there's a functional relationship and we do not have the math skills or tools to actually express or to find the functional relationship, then it might be a good idea to approximate the functional relationship with here the Taylor series expansion. So what we did here is actually a Taylor series expansion. Alright, so now we are finished with this session and I hope you enjoyed it and see you in the next session. Bye.